Hello, everybody. My name is Michael, and today I want to talk a little bit about what me and my group have done over the course of the summer with respect to projective representations. So before we get started, I'm going to give you a good amount of background information just to get you into the spirit of what exactly it is that we're doing. So let CDG be the set of degrees of irreducible characters of a finite group G. In the past few decades, people have realized that if the set CDG is sufficiently nice, then we can actually extract a good amount of information about the group G itself. And I'll give a couple of examples, which we'll also see later. So first, if G is a non-solvable finite group such that CDG consists only of prime powers, then G is either the alternating group A5 times some abelian group or the projective special linear group PSL28 times some abelian group. And also, if G is a non-solvable finite group such that CDG consists of only square-free numbers, then there is some solvable R such that G is the alternating group A7 times R. And our goal is to extend these theorems to a very similar structure known as projective representations. So intuitively, when we say projective or projective space, we're thinking about some space that has some notion of identity and some notion of scalar multiplication, and we wish to quotient out by these scalars. So for example, the projective general linear group is the quotient of the general linear group by the scalar multiples of the identity. And this group will actually be closely related to our definition of projective representations, though we won't actually see it. And the reason we don't see it is because we actually reference these quotiented out scalars explicitly. So given a group G, a map into the general linear group is a projective representation if there's some function alpha, which takes two elements of our group and outputs some scalar, such that for all A and B and G, we have xa xb equals alpha of AB times xab. And this function alpha is known as the factor set of X. And you notice first that this defines a homomorphism into the projective general linear group. And also, if alpha is trivial, then this just is an ordinary representation. Now, we say two factor sets are equivalent if we can get one from another by multiplying the matrices in X by scalars and adjusting the factor sets accordingly. And we say that two projective representations are equivalent if we can get one from the other by both multiplying the matrices in X by some scalars and also conjugating all of them by some fixed non-singular matrix. And we call a projective representation irreducible if it is not equivalent to one of the following form. And if you're familiar with irreducible representations, this should look relatively familiar. And this allows us to classify the irreducible projective representations of a group G with a given factor set alpha up to equivalence. And we let CD alpha G be the set of their dimensions. And if alpha is trivial, then this is just the formally defined CDG. So before we continue, we're going to give a little bit of information that might allow us to relate ordinary and projective representations. So in particular, let N be a normal subgroup of G, and let lambda be an irreducible representation of N. Then the irreducible representations of G pipe lambda are the irreducible constituents of the induced representation lambda G, and CD of G pipe lambda is the quotients of these dimensions with the dimension of lambda. And since N is normal, these are all going to be integers. Now, given a finite group G, there's some finite group gamma, which is an extension of G known as the Schur cover, which satisfies the following. First of all, quotienting out by the center gives us the group G, which is the group we care about. And also for any factor set alpha, there's a unique representation of the center such that CD alpha G is CD of gamma pipe lambda. And this also gives us a partition of the irreducible representations of gamma by the factor sets of G, which actually has equal size if we weight by the sums of the squares of the dimensions. In order to prove statements about the projective character degree sets CD alpha G, we can actually look at existing knowledge about ordinary character degrees using these Schur covers. And with all that out of the way, we can now give you the conjecture that we're actually attempting to prove. So if you remember, when we started, we gave two facts about character degree sets, one regarding prime powers and one regarding square-free values. And if we replace CDG with CD alpha G for some arbitrary alpha in either of these theorems, we have proposed generalizations. And the first of these generalizations regarding prime powers has actually been proven. And we wish to use the same logic of that proof to generalize the other theorem. So in particular, we wish to show the following. Let G be a non-solvable finite group with some factor set alpha. If all of the elements of CD alpha G are square free, then G is some solvable group times the alternating group A7. And Again, using sure covers, we can actually translate this into a theorem which will prove our conjecture and only looks at ordinary characters. And that's as follows. Let G be a finite group with a normal central subgroup L such that G over L, which is the group we care about, is non-solvable. And let lambda be some irreducible representation of L. If CD of G pipe lambda consists of square free numbers, then G over L is expressible as some solvable group times the alternating group A7. So we have a 3-step plan for proving this problem. And what we want to do is we want to consider a counterexample which has the minimum value of the group we care about, which is GL. And for notation, we're always going to let N be the maximal solvable normal subgroup of G. Now we want to show first that G over N is simple. And we then wish to show that for some irreducible representation of N pipe lambda, it's going to be G invariant, which just means that if we conjugate by elements of G, we get the same representation. And it's actually known that this will imply that G over L can be simple, and that CD of G pipe lambda will be the projective character degree set of some finite simple group. And with this will allow us to consider only projective representations of finite simple groups, or ordinary representations, so they're sure covers. And we've actually proved the first of these 3. And while we haven't proved the other 2, we've made significant progress, which is somewhat interesting. So we'll take a look at that as well. But first, let's go ahead and give our proof that G over N is going to be a simple group. So if not, there's some minimal M containing N that is not equal to N that is a normal subgroup of G. And this is going to imply that M is non-solvable. And by the minimality of G over L, we have that M over L is going to be N over L times the alternating group A7, because we can induce their characters to get irreducible representations of G pipe lambda, which will also have to have square free degrees relative to lambda. Now, let AM be the corresponding group such that AM over L is congruent to A7. If M is not unique, then we can also generate a similar AK such that AM AK over L is actually going to be the direct product A7 times A7. And we're going to use a couple of theorems to get a contradiction out of this. First, if N is a normal subgroup of G and lambda is an irreducible representation of N, then CD of G pipe lambda contains only values co-prime with P, only if the CeLO P subgroups of G over N are abelian. Now, it's known that the CeLO 2 subgroups of the alternating group A7 are dihedral and namely not abelian. So that means we can apply this to CD of AM pipe lambda, and then CD of AM AK pipe some resulting character or some resulting representation of AM. So this is going to give us a multiple of 4 in CD of AM AK pipe lambda. And this is obviously a contradiction, so M is unique. Thus, the centralizer of M over N and G over N would either have to contain M over N or be trivial. And since it can't contain M over N, it has to be trivial. And thus by the normalizer centralizer theorem, which implies that the normalizer quotiented by the centralizer is a subgroup of the automorphism group of M over N. And the fact that we know that G over N is not simple by our assumption, we're going to have that G over N is congruent to the automorphism group S7 of A7, where this is the symmetric group. And to finish out our proof, we need one more theorem. So in particular, let L be a normal subgroup of G, let lambda be an irreducible representation of L, and let IG lambda be its inertia subgroup, which is the largest subgroup which fixes lambda under conjugation of elements in G, or maybe and is fixed under conjugation of elements in this group. Then CD of G pipe lambda is going to be the index of our inertia subgroup times the elements of CD alpha of the inertia subgroup over L for some factor set alpha of the inertia subgroup quotiented out by L. And this implies that there's some irreducible representation of AM pipe lambda, whose dimension is 10 times that of lambda, just because we know the projective character degree sets of the alternating group A7. These have already been calculated. And this means that the index of our inertia subgroup actually has to be odd. And that means that when we quotient out our inertia subgroup by N, we actually have to get S7 because we know it contains A7. And if it was merely A7, then our inertia subgroup would have even index. Now note that any automorphism of G yields an automorphism of AM, which fixes L. And this means that if we choose some automorphism corresponding to an element of the symmetric group, not in the alternating group, but still having order 2. This allows us, using that automorphism, to construct a group AM semi-directed with the cyclic group Z2, which is not necessarily in G or G over L, but within which mu is G invariant, and in which this group quotiented by L is going to be S7. And because this is G invariant, that means that since all cyclic groups have only one factor set, which is trivial, and all the representations of cyclic groups have dimension 1, this means that this would give us a projective representation of S7 of degree 10, which is going to give us a contradiction. So now that we've shown that G over N is simple, we're going to give a little bit of insight into why we think G over L is simple. So first of all, by the theorem we just showed, if our inertia group is all of G, then we're pretty much done. So that means it suffices to show that some element of the irreducible representations of n pipe lambda is G invariant. And we consider the possible square-free values of this index. If the index is even, then that means that CD of the inertia group pipe nu consists of odd integers, and that restricts the possible values of this quotient pretty significantly. And the subgroups of the simple groups of odd index are also relatively small in number, though not quite small enough to finish this proof. So we expect to reduce this consideration further using similar methods. So we'll spend the remainder of the talk discussing strategies for simple groups G over L, which, although they can't necessarily prove our generalization without this step of G over L being simple, they are interesting in their own right. In particular, one of the most famous character degree related conjectures, which is Hoopert's conjecture, only considers itself with character degree sets of simple groups. So first of all, we claim that any counterexample G over L cannot be a finite simple group that is not of Lie type. Or in particular, we won't quite look at the group A7, but we will show this for every other group. A7 we'll have to look at separately, obviously, since it has a special relationship to this theorem. But if n is greater than 8, then there is only one non-trivial factor set of the alternating group AN up to equivalence, and there's actually a known representation of it, which has a degree a multiple of 4. This is one projective representation in particular. And since the trivial factor sets fall under the original theorem, this tells us that these alternating groups cannot be counterexamples. And for the sporadic groups, we actually have the character tables of the Schur covers of these groups. And they're actually in the form that they're given in the atlas, which is this reference 3 here. They're actually partitioned by the sub-extensions of the initial group, which are the sub-extensions of the Schur cover, which is sufficient to determine the factor sets that they lie in. And just by brute force on these sporadic groups, it can be seen that none of these actually can yield a counterexample. And now we give one example that we have actually shown that is of Lie type that cannot be a counterexample. And to do this, we have a generalization of what hopefully is a well-known fact if you're familiar with irreducible representations. For all finite groups G and factor sets alpha of G, the sum of the squares of the character degrees is the order of the group. And again, if alpha is trivial, this is very well known. So this means that, say that there are n inequivalent factor sets of G, and let gamma be the Schur cover. If the square sum of the character degrees of gamma, which have square factors, is more than n minus 1 over n times the order of the group, then we can simply apply the pigeonhole principle. And this means that G cannot be an exception to our group, since each one of those partitions, just by the pigeonhole principle, has to have some representation whose degree has a square factor. And the reason we have the groups E6 and E7 is, one, they have non-trivial factor sets, and two, we actually have a website which lists the character degree sets of these Schur covers as functions of Q. And we can run a quick Java program on this to show that this is actually going to apply that these sums, these square sums of these character degrees is actually always going to be more than n minus 1 over n times the order of these Schur covers. And this means that these groups cannot be exceptions. And this is currently our one of our most promising methods of attack to considering the classical groups and the other exceptional groups as well. In particular, we know some of the information about the irreducible characters of the Schur covers of other finite simple groups of Lie type. In particular, for every such cover, there's a closely related group known as the dual group. And there is a subset of this, which are known as the semi-simple conjugacy classes. And this is particularly fruitful when this is classical, when these finite simple groups are of classical type. And some subgroups of these duals have some of their irreducible characters deemed unipotent. We won't go into this exact definition, but we will show why these are interesting. In particular, we have a classification of the irreducible characters of our Schur cover by semi-simple elements of our dual group, and in particular conjugacy classes of them, and unipotent characters of the centralizers of these groups. And we also know that the dimension of this character is going to be the product of some function of S and the corresponding unipotent character. And when we say semi-simple element, we mean only up to conjugacy class. And we wish to show that most of these characters, chi S, have square factors, and each conjugacy class S corresponds to roughly the same square sum. So luckily for us, it is actually known that chi S of 1, which is the dimension, is actually the part of the index of the centralizer co-primed at the characteristic of the group. So in many cases, the classification of all of these centralizers is actually known. And furthermore, there's an explicit formula for the corresponding square sum. All this information together is roughly known as Deligne-Lustig theory, at least how it's relevant to us. And this leaves us only two steps. One is to work out the mechanics of this formula to determine the closeness of these square sums, and also to show that most of these centralizers have square factors in their indices. And what we've seen from this so far, this seems like a relatively viable plan, especially in groups with large numbers of factor sets. However, with that said, some of these formulas are dense and hard to evaluate, but luckily most of the ones which have small numbers of factor sets. And what this means is if there are n inequivalent factor sets, it actually only suffices to find n-1 projective representations of different non-trivial factor sets whose degrees had square factors, or n-1 corresponding ordinary characters of the Schur cover, of course. And one of these that we have in mind is known as the Weyl representation. And in groups of type B, for example, with dimension n and corresponding finite field FQ, there are 4 Weyl representations, and their degrees are q to the n-1/2 and q to the n+1/2, each with multiplicity 2. Now, when q is odd, there are 2 factor sets of these finite simple groups up to equivalence. Now, if we could show that these factor sets split up these representations of equal degree, then this would mean that whenever n is even, or q is 1 or 7 mod 8, that one of these degrees would have to have a square factor. In particular, would have to be a multiple of 4. And this means we could ignore whenever n was even or when q is equivalent to 1 or 7 mod 8. And while there are other such representations we consider, this one illuminates enough of the information that it's not really worthwhile to look at the others here. But that's all I've got. I'm going to leave some references here. And thank you so much for coming. All right. Let me go ahead and stop recording if I can figure out how to do so. All right, thank you.